Hello everyone again and welcome to Machine Learning Tips. Today we are going to be starting supervised learning properly, where we are going to go into details, the different types of supervised learning, where we are going to look at regression problems and classification problems. As a recap, supervised learning is a type of machine learning where the model is trained on what label data, meaning that for every input there is a corresponding what output. So the goal of supervised learning is to map some function uh, that maps elements from what from x to what to y. So this element from x to y that can predict output forward for new unseen inputs. Where here we are having x here, we can have input futures. There can be many of them. Like it could be the size of the house, it could be years of experience based on salary, and then the target variable here could be the size of that price of that house as well as what the salary. So the general form of the equation for supervised learning is y is equals to f of x because it's mapping elements from some x to y plus what is error term. As I did mention, most of the times we'll be trying to reduce this error as much as possible, whether it's a regression problem or classification problem. So here, x here is the target variable in terms of regression problem. We have the input futures, and then we have that function f of x, which the model's mapping function. And then we have that error term, which could be like a noise made up of the variance and bias. So the first kind of supervised learning we are going to be starting with is what we call linear regression. Linear regression is used not only in machine learning, it is a statistical technique which which models the relationship between a dependent variable, which is like that target variable I did mention, and one or more independent variables, which is what the x using what a straight line. This straight line should simply tell you that with linear regression, it can only work for problems where there is a linear relationship between what that dependent variable, which is the target variable, and the different input variables. We are going to see how to look at this relationship when we grab a real world data set and then we try to do some exploratory data analysis with it and then see whether we can fit a linear regression model in that scenario. So here the linear regression can help us answer questions like, how does y change when x changes? Because when we plot a graph, we can actually interpret this kind of answer this kind of questions, especially for graphs that we've seen mostly like the graph of y equals to mx plus c, which is like a straight line graph. So the equation here for linear regression as a starter is always of the form y equals to beta 0 plus beta 1x plus what that error term. So we are trying to reduce this error, which will be the difference between what when we are able to find this to get the values for this beta 0 and beta 1, we can now come out with an equation and then use that equation to predict if it was the salary of people based on years of experience. Every time we have a year of experience, we can always predict that salary because we already have that estimated equation. So the intuition behind linear regression is to what? Like, first of all, trying to imagine plotting points on a graph, which could be the size versus what? Price. And then also linear regression will now do what? Fit a line that minimizes the difference between what? The actual values and what? The predicted values. Actual values here will be if it's like using years of experience to predict salary. The actual values here will be what? The first data set that we had for every year corresponding to their salaries, and then the predicted values will be when we estimate these parameters beta 0 and beta 1, we will now be able to do what? To predict the salaries of someone based on what? This input, which is what? Years of experience. So that difference that we are trying to minimize, which is what we call this error as we move ahead, is also called what? The residual. So most of the time we are trying to minimize that the square difference between what? Those predicted values and what? And the actual values. So as an example, let's say we just generated some data where we are having X here, which is the years of experience, and then Y to be what? Their salary. And then we try to plot this graph to see how it looks like. So we can see here what we are talking about. The blue lines here will be what the actual uh, values, and then this red line here is actually showing that predicted line where it's fitting the relationship between what salary based on what years of experience. And then we can see here, these dotted lines where the difference between what where these actual values meet the predicted value is what we call the residual, which is actually the difference where we can map this, look at this value here, subtract from this, it will give us something like this, and then at the end we are squaring these residuals and looking at what their mean, which is what, as we move ahead, is what we call what the mean squared error, which we use that as a cost function to for regression problems. So why is linear regression very necessary? It's good because it's what is simple and easy to interpret, because from this graph we can actually see that as years of experience increases, what happens? The salary will also increase. It works well when there is that relationship in what is roughly linear. When we can estimate this problem that there is a linear relationship between what years of experience and salary, and then we can roughly use linear regression. It's a building block for what more complex models. So before we go into different complex models, as models that are non-linear, it's always good to start from what? From linear regression to understand why are we even going into those complex models. Where can we use linear regression? Predicting sales from ad spend, predicting salaries based on years of experience, also forecasting crop yield from what? From rainfall. We can also use it to do what? To predict house prices based on the size of the house and so on. So the key concept here is what we call the intercept, which is a starting point value of y when what x is 0, and beta 0, which is the rate of change. Positive is equals to what? Increasing relationship. We can see here that it is an increasing relationship, but there are cases where once maybe years of experience will be increasing, what will happen? The salary might be what? Might be decreasing or something like that. We are going to see such problems. The limitation with linear regression is that what? It assumes that linear relationship. So if that is not going to hold, it will not be good for curves, because curves are non-linear. It is very sensitive to outliers. Let's go back to this graph. Let's say we have some points that are very far away from this line. Then those points will be what? Will be pulling this predicted line towards those points, and then in that case, these residuals will be very, very high. So if the residuals are very, very high, then the difference between the observed and the predicted value will also be very high. And then in that case, linear regression will not be a good fit for such problems. Another disadvantage that we have with linear regression is that it captures correlation and not causation. Causation here is cost. Let's say we were having cases where there is some strong linear. Let's say we had two futures, like years of experience and then size of the house, or maybe so in that case, if there is some strong relationship between years of experience and maybe the level of education, let me use level of education in this case, and then it will be a problem because these two futures are very correlated. So we are going to see how to deal with cases when the input futures are having a strong correlation as we move on with linear regression. Now, when we will be training models for linear regression, what we are going to use as a cost function is what we call the mean squared error. The mean squared error is what we use to minimize that difference between what the predicted and the observed value. You see, because we are having many of those values, so we at the end we are going to be looking at what a square difference between the observed and the predicted value, and then we look at their mean. So most of the times we want to minimize this error as much as possible so that we can say that model is a good fit or not. Another thing that we move ahead is what we are going to see is what we call the root mean squared error, which is like the square root of the mean squared error, which is also what we can use to evaluate whether a regression model is a good fit or not. So as for the start, we will must be using most of these math concepts to understand how linear regression works, or most of the machine learning models work. But most of the times we'll be using this library, which is called scikit-learn. You can read more about this to feed most of these models. So from scikit-learn, you can import linear model, which in that case you can import what? Linear regression. Also from scikit-learn, you can import what we call metric. This metric here, as we move ahead, is mostly used to evaluate models. You can import the mean squared error. And then we are going to use model selection, where we import what? Train test. This train test is going to be used a lot, especially when we have a large data set and we need to split it in such a way that we have data to train the model, and also hold part of that data to do what? To test and see how the model is performing. So when we do that, we can call that linear regression model here, and then feed it with what? That input feature, which is what? X train and what? Y train. And then we can do a prediction. So a prediction here is, based on the year of experience, can we be able to estimate what? The salary of someone. So if we bring this, we will have this output here. We pick year of experience as what? As someone that has 3 years of experience. What will be the salary? That is why here we are having. So this X test here is what these 3 years of experience, which is 3. And then when we try to predict, when we feed this model, we are seeing that someone with 3 years of experience, the salary is approximately what? 61,107 US dollars. If we go back to this our graph, we can see here that if we are trying to pull, let's say 3 is here, and we are trying to extrapolate from this graph, we will also find that it falls between what? This predicted value, which is around 61,000 something, if we are trying to extrapolate. So guys, that was it for this lesson today. So also we also measure the mean squared error here. It's pretty high. As we move ahead, we are going to see real world problems on how to reduce this mean squared error. We are seeing that this mean squared error here is high because if you look at this graph here, it wasn't really a good fit, because this predicted line here was not really picking most of these actual points. The only point it came closer was this blue line here, which was around 59,000 or so. So that is why the mean squared error for this model is pretty high. So guys, that was it for today. Tomorrow we are going to look at different variations of regression, and from there we are going to move to some real world applications on how to build models and then do some predictions with them. Thank you so much. Keep following me for more of these tips, both on Facebook as well as on YouTube.